Welcome to my lecture on sequences. Okay, and here's what a sequence is. I'll give you the definition. It's any list of numbers with an order. Okay, and the domain doesn't have to strictly be the counting numbers. There's variants of that, but it's equivalent. Let me just give you our first example of a sequence. Okay, a sub n is going to be equal to 1 over n. Okay, and this starts with n equals to 1. That's a counting number, 2, 3, etc. And it goes on to infinity. So two things. One is I don't have to start this sequence at 1. I could start it at 2. I could start it at several different numbers. So that's the variant on the domain. The second thing is that this is a restriction of a function. So if we let f of x be equal to 1 over x, the sequence a sub n is just the restriction. So that is if we took f of x, but we just input x equals 1, 2, 3, and so on. Then we'd have exactly the same sequence. So sometimes sequences can be functions. Okay, and in this instance, a sub 1, well, that is equal to f of 1, and that's 1. A sub 2, that's going to be f of 2. This is going to be 1/2. A sub 3, similarly, is f sub 3, which is going to be 1/3. And here's a natural question that gets asked a lot in sequences, which is, what is this limit? Okay. Well, this is just this limit as n goes to infinity of 1 over n. And this, we calculate this limit in exactly the same way. Exactly the same way that we would the function. And that is, we think of this as being 1 over a very large number. And 1 over a very large number gets closer and closer to 0. So that's equal to 0. Okay. Now, here's going to be another convention or definition, and this one we're going to use a lot. We say the sequence a sub n converges if this limit as n goes to infinity of a sub n is finite. Okay, equals L, and L is finite. Okay, so in this example that I gave of a sub n being 1 over n, it converged, this sequence converged. Okay, otherwise, okay, we say a sub n is divergent. Okay. So a couple keywords, convergent and divergent, boils down to computing the limit of the sequence. Okay. Now, I want to go over a few more examples of sequences, but here's a few properties of sequences. And it's just kind of important that I write down this list so that you know that you can use it, but I'm not going to discuss too many of these abstract properties. I'm just going to use them from time to time. Okay. And they're more or less properties of limits that we already know. So this first one is that a limit of two sequences, this is equal to the sum of the limits of each sequence. Okay, that's the same calculus 1 rule that we had. Okay. 2 is that the limit of a constant times a sequence is the same as the constant times this limit of the sequence. Okay. Our third one is that this limit as n goes to infinity of a sub n times by b sub n, this is the limit, the multiplication of the limits. So and this one also is more general. So if you have division, this implies that you can take the limit of an over bn is also the limit of an divided by the limit of bn. But this is implied by this property 3. So I'm just going to write the single property. Okay. The last one is that if I have a limit of a sequence to a power, this is equal to the power, the limit taken to the power. Okay. So just a few properties that translate over from calculus 1. Basically, calculating limits is the same as we would in our calculus 1, and that's very nice to know. But here our limits have to be infinite. Okay. Now, there's another property from calculus 1, and it's called the squeeze theorem that works. Now, this squeeze theorem, this one's very important. Okay. So the squeeze theorem says that if we have this situation, we have two inequalities with 3 sequences, then the limits obey this inequality. And this is a very, very important theorem. And this next one is a consequence of the squeeze theorem. It says this: if the absolute value of a sub n is convergent, then the original sequence is convergent. And this is a direct application of the squeeze theorem. Here our lower bound would be minus a sub n, and our upper bound would be the positive one. Okay, so our rules of calculus apply. I want to emphasize here that right now we were able to calculate the limit. Like in this very first example, we said that the limit was 0. The limit as n goes to infinity of 1 over n is 0. That's great. But there are going to be instances in which we only ask if it converges or diverges, and we won't be able to compute explicitly what the limit is. Okay. Okay. Now, some things that help us calculate limits determine, not calculate them, but determine if they converge or diverge are the following theorems that I'm going to write down. But first I need two definitions. Okay. And it's these two definitions boil down to this thing called the monotonic sequence theorem. Okay, so let me give you two definitions, then I can state this theorem. So it's just this notion of increasing. So that is increasing if the larger term, n plus 1, an plus 1, is bigger than the previous term. And this obeys the property for every single input n. So I'm just going to say for all n. Okay. And it's called decreasing, so i.e. increasing means this, A1 would be bigger than A2, would be bigger than A3, and the trend continues all the way to AN, and it continues even beyond A sub n. So for example, A sub n plus 1 would be bigger than A sub n. So this would be increasing. Okay. So a sequence is decreasing if I just flip the inequality. So it's decreasing if A sub n plus 1 is less than A sub n, okay, for all n. Okay, so decreasing and increasing, two terms you need to know. So here's one definition, here's the second definition. Now, here's a definition of boundedness, okay? So a sequence is bounded and I should say above, if there's a number such that this inequality holds. So it needs to be less than or equal to this number for all n. So it can never exceed this number, okay? Now a sequence is bounded below and I just changed this inequality. Okay, and if it's bounded above and below, then it's called bounded. So this is below, the other one was above, okay? Okay. And this leads up to this very, very important theorem, which is going to come back to you. And I'm going to probably make you know this one, or I hope to. And it's called this monotonic sequence theorem. Okay. And the monotonic sequence theorem, it says every bounded monotonic sequence is convergent. Okay. And we are going to use this fact a lot. Okay. Now let me go over this with the example that I used earlier. Okay. And by the way, monotonic means strictly increasing or strictly decreasing sequence, one or the other. Okay. Okay, so here I'm going to give you a sub n. This is going to be 1 over n. And n begins at 1, 2, 3, 4, so on. Now, certainly, I think we'd agree a sub n is decreasing. It's a decreasing sequence. And this is because if I look at a sub n, that's going to be 1 over n, and that's bigger than a sub n plus 1 because its denominator has increased. I'm dividing by something slightly larger. Okay, so it's decreasing, and I think you'd agree a sub n, because it's decreasing, is always smaller than its first term, which is 1. So that's equal to a sub 1. Okay, now by the monotonic sequence theorem, since a sub n is bounded above, okay, and it's also bounded below because this a sub n always has to be positive. Whatever n is, even if it's a billion, it's still bigger than 0. So it's bounded, okay, bounded because of this relationship. And decreasing. A sub n is convergent. And we're done. If the question asks, does the sequence converge or diverge? We answered the question. Okay. Now, this was a brief introduction to sequences. I'm going to go over a few other examples of sequences, and that is pretty much going to be the gist of sequences. This is your very first introduction, your very first example. And what I want to emphasize is that sequences, they're things that are very familiar to us. They're functions, but some of them are functions that have input being these integers, 1, 2, 3. They could start at 2 or they could start at 5. They could start, their starting point could be arbitrary. We could ask if they converge or diverge, equivalently their limit. Okay, but we don't need to compute their limit explicitly to answer the question, does it converge or diverge? A lot like improper integrals. Okay, and we're going to use that fact a lot. Okay, we're going to use this monotonic sequence theorem. Okay, thank you very much, and I hope to see you again soon.